The last lesson showed why we have QFE, QNH and flight levels as possible altimeter settings at different stages of flight. In this lesson, we shall examine how and when we change from one to another. This is called altimeter setting procedures. We will also explain density altitude, which is a different concept from pressure altitude, but it can cause confusion if the difference is not understood. But first, we will look at the definition of QNH in more detail. You will remember that we defined QNH as the subscale setting that will cause the altimeter to read the airport elevation when the aircraft is at touchdown. We also said that, broadly, it gives a pilot his altitude above mean sea level, but that is not the correct definition because of the possibility of temperature errors. The definition to be used is always the one we have just given. Let's see why there's a difference. Imagine an aircraft on the runway at an elevation of 270 feet. And we'll assume that the QFE is 995 hectopascals. The ISA pressure lapse rate at mean sea level is 27 feet to a hectopascal, which equates to 10 hectopascals for 270 feet elevation. At the ISA temperature of plus 15 degrees at mean sea level, our QNH would be 1005, 10 more than the QFE. And, under these conditions, our altimeter would correctly give us true altitude above mean sea level. However, remember that we said that temperature changes cause the pressure layers to expand in width. Suppose that we had such a high temperature that 30 feet of this warmer air was needed to change the pressure by 1 hectopascal. In that case, 270 feet of elevation would change the pressure by only 9 hectopascals down at sea level. So the actual pressure at mean sea level would be 1004. We call this the QFF, and you will learn more about it in meteorology. However, our altimeter does not know about the temperature. It is designed to always give us 27 feet to a hectopascal at sea level. If we want it to read 270 feet at touchdown, we must set it to QNH. If we now fly down to sea level, as we touch the water, it will sense 1004 hectopascals and tell us that we are still at 27 feet. Therefore, QNH is defined as that subscale setting which will cause the altimeter to read the airport elevation when the aircraft is at touchdown. It is usually very close to the value which gives 0 feet at sea level, and, unless the temperature deviation from ISA is large, it is usually close to true altitude, but neither of these are correct definitions. We'll now look at when and how we change our pressure settings. There are procedures in place to ensure that aircraft are using either QNH or flight levels as required at agreed altitudes, so that we do not get aircraft at similar altitudes on different pressure settings. At the airport of departure, we use either QFE or QNH as we prefer. However, once away from the airport air traffic zone, we must be on QNH for the initial part of the climb in order to ensure safe clearance from high ground or obstructions. At an agreed altitude, we set 1013, otherwise known as standard pressure setting. This altitude is called the transition altitude, and its actual value varies from country to country and region to region. In the UK, transition altitude is usually 3,000 feet, except in some major airport control zones where it may be 4,000 or 5,000 feet. However, other countries use different figures. In the United States, for instance, transition altitude is 18,000 feet. It makes sense for the US to use such a high figure. In general, it is a good idea to be on QNH when in the vicinity of high ground. There are peaks well over 14,000 feet in California and the Rockies, and over 20,000 feet in Alaska. The transition altitude is, as the name suggests, an altitude. In other words, it is based on a vertical distance from mean sea level. This means that in any given region, it is a fixed value and does not depend on the QNH. If the QNH is, say, 1013, then a transition altitude of 3,000 feet will correspond to a barometric pressure of 908 hectopascals. This is a change of pressure of 105 hectopascals. However, if the surface pressure changes and QNH is now 990 and the subscale setting is set correspondingly, then the altimeter will sense 3,000 feet at a pressure of 885 hectopascals. This is still a difference of 105. Therefore, the vertical distance of the transition altitude from the surface does not vary with surface pressure. It is the same from day to day, and so it can be permanently published in aeronautical information documents. Let us assume that we have conducted the main part of our flight above the transition altitude and have been using flight levels. We now wish to descend. At some point we must set QNH again. This point is called transition level, and, just as transition altitude was used only for the climb, transition level is used only for the descent. The reason is obvious. Your altimeter must be set to the datum you are using at the time. Near the ground, on the climb, this is QNH, which is an altitude. Therefore, it must be an altitude, not a flight level, which prompts you to set standard pressure setting. On the descent, however, you have flight levels set as your datum. Therefore, it must be a flight level, not an altitude, which prompts you to reset QNH. Transition level is the first available flight level above transition altitude. Therefore, transition level is the flight level at which we reset to QNH on the descent. Clearly, as it is a flight level, its true altitude will vary from day to day or even hour to hour, depending on the difference between the surface pressure level and 1013. Because of this, it has to be calculated by air traffic control, who will have the latest surface pressure, and the transition level is passed to the pilot shortly before the descent. In fact, they even tell you that it comes from ATC on the published document in this example. The difference between the transition altitude and the transition level is called the transition layer. Different countries use different rules to establish its thickness. In the UK, it must be less than 500 feet above the transition altitude. In some other countries, it must be not less than 1,000 feet. In any country, the thickness of the transition layer depends on the relationship between QNH and 1013 hectopascals. In the UK, it has to be between 0 and 499 feet. We will now go on to consider the actual definition of pressure altitude. You'll remember that we said that, in practical terms, it is the same as flight level. In other words, if you set your subscale to 1013 and do not correct for temperature error, your altimeter is indicating pressure altitude. However, let's look at the basic definition of pressure altitude and try to understand it. The definition is: pressure altitude is that altitude in the international standard atmosphere at which the aircraft's current actual barometric pressure would be sensed. Imagine that you are in an aircraft and, on that day, in a particular atmosphere, at a true altitude of, say, 9,700 feet, there is a combination of barometric and temperature errors which gives you an atmospheric pressure of 697 hectopascals. Now, if we look at ISA, we see that, in the ISA atmosphere, 697 hectopascals occurs at exactly 10,000 feet. Therefore, our pressure altitude is 10,000 feet. The ISA atmosphere is based on a surface pressure of 1013 and a defined temperature lapse rate. Our altimeter is calibrated to the same law. Therefore, if you set 1013 and don't correct for temperature when it senses 697 hectopascals, it reads 10,000 feet. This is the same thing as pressure altitude. Now let's look at density altitude. This is quite a different concept. The definition sounds very similar. Density altitude is that altitude in the international standard atmosphere at which the aircraft's current actual atmospheric density would be sensed. However, density altitude, unlike everything else we have discussed previously, has nothing to do with vertical distance. It is a measure of aircraft performance and engine power. Air density directly affects engine power. Air is drawn in through the intake and mixed with fuel, which is burnt in a cylinder or combustion chamber, where its volume is greatly expanded. This expansion is partly caused by the addition of fuel, but mainly caused by a large temperature rise. In order to achieve correct combustion, the fuel-air ratio has to be correctly controlled. The fuel is mixed with the oxygen in the air in a ratio which is defined by weight. If the air is dense, more fuel will be provided and more power will be available. However, if the air is less dense, less fuel will be provided in order to maintain the correct mix. Therefore, less power will be produced. This can have a considerable effect, particularly on takeoff performance. If the pressure does not change, density is a simple function of temperature. Let's see what effect this can have. Suppose that you are at Nairobi Airport and that the pressure altitude is 5,500 feet, which is also Nairobi's true elevation. We will assume a temperature at the airport of plus 35 degrees Celsius. Nairobi is on the equator. One way of finding the density altitude is by use of the navigation computer. We start with the airspeed window. Set 5,500 feet against plus 35. Here it is, slightly magnified. Now, without moving anything, look in the density altitude window. Here it is again, magnified as before. You can see that it indicates just above 9,000 feet. This is your density altitude. This means that at a pressure altitude of 5,500 feet, your engines will only develop the thrust in an ISA atmosphere at over 9,000 feet. This will make a significant difference to your takeoff performance. If you didn't have your navigation computer to hand, get it out now and run this scene again as many times as you need to in order to become familiar with the process. Another way of finding the density altitude from pressure altitude and temperature is by use of a simple equation. The equation is density altitude equals pressure altitude plus ISA deviation times 120. The actual conversion factor is 118.8, but 120 is close enough for any practical calculation. Nairobi's pressure altitude was 5,500 feet. That is an ISA temperature of plus 4. Click when you're ready to go on. So, if ISA is plus 4 and the static air temperature is plus 35, what is the ISA deviation? Click when you're ready to go on. You should have come up with the answer plus 31. Now let's substitute into our equation. Pressure altitude is 5,500. The ISA deviation is plus 31. That gives us a correction of plus 3,720 feet. Our density altitude is 9,220 feet. You should use the equation in preference to the navigation computer in examinations, when the answer options may be too close to separate with the navigation computer. However, the computer is always good enough in any real-life situation. Let's summarize what we covered in this lesson. We started by showing that when QNH indicates the airport elevation at touchdown, this is not necessarily 0 feet at sea level and not necessarily true altitude, but it is usually close. We explained that transition altitude is the point at which we change from QNH to flight levels on the climb. We also said that it did not change with the QNH and so can be permanently published. Transition level is the point at which we change from flight levels to QNH on the descent. It varies as the QNH changes and so has to be calculated by air traffic control. It is passed to the pilot shortly before the descent. The airspace in between is called the transition layer. The thickness of the transition layer depends on the relationship between QNH and 1013 hectopascals. In the UK, it has to be between 0 and 499 feet. Pressure altitude is defined as that altitude in the international standard atmosphere at which the aircraft's current actual barometric pressure would be sensed. In practical terms, if you set your subscale to 1013 and do not correct for temperature error, your altimeter is indicating pressure altitude. It is the same thing as flight level. Finally, we examined density altitude. This has nothing to do with vertical distance. It is a measure of aircraft performance and engine power. It is defined as that altitude in the international standard atmosphere at which the aircraft's current actual atmospheric density would be sensed. We can establish it by use of a navigation computer. This is satisfactory in any practical application. However, in exam questions, if the answer options are close, use the equation.